Welcome to Mr. Hobbs AP Chemistry class. This is Monday, December the 5th. This is part 2 of our discussion on enthalpy of reactions. Alright, so we then determined that it takes 1415 kilojoules. It takes, in order to make 96 kilojoules of energy, we have to decompose or produce 6.43 grams. Now, on D, we want to then go, okay, we want to decompose it. So that means we're going to have to put the energy in. So again, what happens to the sign? It just changes because products have become reactants, reactants have become products. So if we want to then figure out how much energy is released, or in this case absorbed, okay, so what do we start with on D? .5 grams of MgO. What do we need to convert that to? 1 mole over 24.3 grams. Why not the 2? Why don't I use 2 moles there? Because you don't. Because when you're converting to moles, it's always the grams per 1 mole. 24.3 is the grams in 1 mole. And now we know how many moles we have. We have this fraction of a mole, about 1/3 of a mole. Okay? And so, now what? What's our conversion factor now to be able to go to, what are we looking for? Okay, 1204 kilojoules, so where does moles need to go? On the bottom. So you're going to say 2 moles of MgO. Now, if they mentioned oxygen, it would just be 1 mole. It's whatever the coefficient is in front of the thing that you're looking for or given. And then it's going to be a positive 1204 kilojoules. Because we're going the other direction. Oh. Yep, it should be. Just seeing if y'all are awake. That's the given in the problem. 7.5 grams, how much energy is going to be absorbed and causing it to be decomposed? So what does this come out to now that we've adjusted the numbers? 112? Does somebody agree with that number? And we can just go with 112 since we really only have 2 sig figs here. 112 is good enough. Kilojoules of energy absorbed. Okay, so since it's positive, that's how much energy it's going to take to absorb it. So if we want to look at just this graphically, with potential energy on the y-axis, reaction progress down here. Okay, so we're saying that the reactants go to products, so it's Mg plus O2 here going to 2 MgO here. So obviously the MgO has much less energy. What is this value going to be? From here, going left to right, what is this number going to be here? Negative, but negative what? 1,204. That's my delta H of the reaction. Okay, so that's going to be this right here. So what's my EA? Energy of activation, what's that going to be? Where do we go from? From here to here, right? So we're going to call this EA forward. So the magnesium oxide has 1,204 kilojoules less energy than the elements themselves. Okay? So we're way down here. But now if I want to reverse this reaction, I want to go right to left. What am I going to have to do in terms of energy to get the MgO back to the Mg plus O2? In terms of energy, what do you have to do? Say that again, sound loud for me here. Okay, so what did she say up front row? Add in 1,204. Okay? So you're going to put in, so the only thing that's different is the sign. Here, to go from here to here, the energy is released, given off. But to go backwards, right to left, you're going to just put it in. It's just the only thing that's going to change is the sign. Because the law of conservation of energy is neither created nor destroyed. We're just changing potential energy here being given off to the surroundings. And so the surroundings get hot, so you're giving off this much energy to the surroundings. But if we want to make it come back, well, the surroundings have to give the energy back, put it back into the system, and go back up to here. So what would be my EA reversed, or the EA to make it go from here to here? The energy of activation. Where does it start from? This bottom here? Here? This dotted line, right? Because this now is my reactant. This is my product. So now my EA reversed is going to be here. Let's try that better, make it better. So when you're doing the activation energy or the reverse reaction of the same reaction, it's just going to be from the bottom to all the way to the top. Let's make this like the reactant and this the product. Okay? All right, just practice one more. See what you can do on number 40. Number 40. Page 207. Okay, we're about done? So what do we think? So what do we start with for A? 0.855 moles of O2. Then what? Over 3 moles of O2. Okay? So then that's going to give me moles of O2 cancel. It's going to give me the number of kilojoules, and what does that come out to? Negative 25.5 kilojoules. So that's how much energy is going to be released if we make 0.855, if this decomposes. And by the way, this is the reaction that we did with the crucible, the percent oxygen in KClO3. We heated it up, decomposed it in order to produce the oxygen. Okay? Now, we had to put energy in order to cause it to decompose, but more energy was released when it actually did the decomposition reaction. Okay? This is, theoretically, we're going to talk about this being a spontaneous reaction, that it occurs all on its own. But because it doesn't decompose a lot at room temperature, because when we just put it in the crucible, it didn't start decomposing, what do you think that means? What would keep it from starting to react at room temperature? Even though it says that it has a negative value, it's exothermic, it's favored in nature, why wouldn't it react right off the bat? Think of our graph. What, Rizwan? What about it? Doesn't have one? It's too high. It's got a high activation energy where at room temperature there's not enough energy for the molecules to get up and over it. Okay? So, but the shelf life for KClO3 isn't indefinite because little by little it does actually decompose because remember, temperature, some are going slow, some are going fast, some are in the middle. Those fast ones might have enough energy to actually decompose. But if a reaction, even though it's favored in nature, a negative, and remember, lower energy, an exothermic reaction is favored in nature, that sometimes they don't react all on their own because they have that high activation energy. So B is basically the same problem. What's the only extra step we have to do? You got to convert it to moles. 1 mole, and it's going to be 39.1 plus 35, 74.6. Times, now what? Over 2 moles of KCl. And that comes out to equal 6.45 kilojoules. Okay, because moles of KCl cancel, leaving you with kilojoules. All right, so we can, once we have the heat of the reaction, once we know delta H, we can then use that in a stoichiometry type problem just as another conversion factor, kilojoules per however many moles are given in the reaction. Okay, so it's just another straightforward problem, just a stoichiometry unit problem. Now, let's look at one other variation of this type of problem. And that's going to be if we turn and look on page 209, number 73. Number 73 says acetone, C3H6O. It burns and makes CO2 in water? Yeah. And it's liquid water, right? H2O liquid. And it's 3 and 3. Okay? But this time it tells us that delta H of the reaction is equal to negative 1790 kilojoules. But what's the question in the problem? The enthalpy of formation. Now again, remember, as soon as we hear the word enthalpy, we're going to translate to heat. Okay? So it's really saying the enthalpy of formation, we're going to translate that to what is the heat of formation. Delta H. Okay? So what are we solving for here? Because we know the heat of the reaction. What's this really asking for? Because remember, delta H of the reaction is going to equal the sum of my delta H of formation of products minus the sum of delta H of formation of reactants. Okay? So delta H is going to equal 3 times the delta H of formation of CO2 plus 3 times the delta H of formation of H2O minus 1 times the delta H of formation C3H6O plus 4 times really 0. Correct? So that's a generic equation for everything that we're going to do. So, let's just make it even in here 4 times, just to be consistent. Delta H of formation of O2. Now, what do we know? What are we looking for? What's my variable here? Let's read the problem. It's very important to know what you're looking for. What about acetone? The heat of formation of acetone. So what is that in my equation? This, right? So this is really my unknown right there. So now I know what's the heat of reaction going to be? What's this value? It's negative 1790. It's going to equal 3 times, we go and look this up in the back of the book as negative 393.5 kilojoules. Let's just do it all right. 3 moles. Negative 393.5 kilojoules per mole. Plus 3 times the heat of formation of water, negative 285.83. Minus X, well, let's just keep it delta H of formation plus 4 times 0. Okay? Does everybody know where everything came from? So now we have to solve for this. So now you just kind of plug it into your calculator. If you have your Inspire calculator, you can just plug that in and just make this X. Or instead of using that, it can be X. Now, will moles cancel out? What did we get? Did we get the same answer? No? Somebody say an answer out. Corey, what'd you get? Come on. Negative 247? That's what she got. Anybody else get that? 0.99? 247.99? Okay, well that'd be 248 since there are no decimals in 1790. Now let's look at the math. Most likely, if you messed up, if you didn't get negative 248, it's because you didn't distribute the negative sign into the bracket. Okay? Now, when we multiply all this out, does anybody have a number for this whole term right here? Does anybody happen to write it down? 2036.49. And that's just going to be kilojoules. This is going to equal negative 1790 kilojoules minus 1 mole times X. Right? So now we have to bring this X over here, so it's going to be 1 mole times X is equal to negative 2036.49 plus 1790 kilojoules. So this is going to equal your negative 248, right? And that's kilojoules. But we haven't isolated X yet. What do we need to divide by? 1 mole, right? So X, which is going to equal my delta H of formation for C3H6O, is going to equal negative 248 kilojoules per mole. So that's going to be per mole. So that's going to be the units on delta H all the time. It's kilojoules per mole. So did you see your algebra mistake if you didn't get the 248? The most common thing is forgetting to distribute the minus sign into that parenthesis and to do the minus X. So sometimes we have to calculate the heat of the reaction. Sometimes we're given the heat of the reaction, we have to calculate an individual heat of formation. Where you just make that your X. So let's just do one more practice like that. Let's look at number 74 on the next page, 210, and just see if you can work that one super quickly. And then I have one more concept that we need to cover. Number 74. Here you go. What's the heat of formation of calcium hydroxide? And for C2H2 acetylene, 226. Minus okay, one big old long equation. So then we have to solve for this. This is the one thing we have to solve for. So when you go through and do all of that, the delta H of formation of C2, what are we looking for? CaC2 is equal to what? Negative what? What are the units on that going to be? Kilojoules per mole. And the mole comes from this 1 mole right here. Now, you don't really need to keep track of the moles all the way through like that. You just know that the answer is going to come out in kilojoules per mole. It doesn't hurt to use your units, okay, and just kind of see, make sure. Whoops, this one doesn't cancel. And then you don't have to put the zeros in when it's an element and all that. Does anybody have any questions about any of this? So far, it's just been plugging into a simple equation and just solving either for delta H of the reaction or our delta H of formation. Okay? And then once we have this value, the delta H, now the delta H of the reaction is the conversion factor. These individual ones don't really help us as far as knowing, like the problems we just did, as far as how much heat total is going to be released. This is the amount of heat that's being released right here. Okay? So we got one more way. A second way to calculate the delta H of the reaction. And that's going to be bonds broken minus bonds formed. But if you know in the notes somewhere way back when in the middle of Friday, I said there are two ways to calculate delta H of a reaction. So far, everything we've been talking about has been this first way, the sum of the heat of formations of products minus the sum of the heat of formation of reactants. The second way is using bond energies. Now, in order to do this actually we're going to jump into Chapter 8 just a little bit. We skipped over this part in Chapter 8 because we hadn't done Chapter 5 yet. But this is all about bond energies. So if you turn to the back of Chapter 8 on page 339, and we look at question number 69. It says that nitrogen gas combines with hydrogen gas, 3 of them, to make 2 ammonia gas. We want to calculate the heat of the reaction using bond energies. So you go to table on page 330. Now I'm not quite sure what page it is in the new book, but this is in the old book, page 330. And they give you a list of all the different bond energies on page 330. So you can see a carbon-to-carbon single bond, a carbon-to-carbon double bond, just a whole bunch of common covalent bonds. And the bond energy is the energy that's released when those two atoms come together, and it's the energy required to break them back apart. Okay? So it's a positive energy going in to break them. It's a negative energy when they're released. But to calculate it, we're just always going to use the positive value of it, and we're just going to plug into this. But you kind of need the Lewis dot structure. If you look at the other questions on that page, they give you the structure because we need to know how many bonds are broken, how many bonds are formed. So when we're looking at this, for nitrogen, how does nitrogen bond to itself? Triple bond, right? We've done that enough now. Nitrogen looks like this. And how does hydrogen bond to itself? Single bonds. And we have 3 hydrogens, so it's going to be 3 hydrogen-hydrogen single bonds. And then ammonia Okay, so ammonia is going to look like that, correct? So if we want to calculate the delta H then, so we're going to have to go with how many bonds are broken, how many bonds are formed. Now, which reactants or products are we going to break bonds? Breaking bonds. Okay? How are we going to get this to make that? We got to break this apart, right? We've got to break these hydrogens apart from one another so they can rearrange and then reform the bonds here. So breaking bonds is always going to be the reactants. You're breaking the bonds. In products, you're reforming them over here. So again, this is kind of like the whole idea. We say that bond energies or heats of reactions is a state function. And all that means is that it doesn't matter how you get from point A to point B. The energy change is always going to be the same. So we're going to look at, okay, we're going to say that delta H, rather than talking about the potential energy here, well, how much energy does it take to break these bonds? How much energy is going to be re-released when these bonds form? So we can assume everything's going to break apart and then come back together again in a new way. So we go then and we say the delta H of the reaction is going to equal bonds broken. Well, how many nitrogen to hydrogen bonds do we have? Nitrogen to nitrogen bond, this triple bond. We only have 1, right? So you go on the chart, what's the value for the bond energy of nitrogen to nitrogen triple bond? So, how to say that again? 941, and that's kilojoules per mole times 1 mole. Plus, how many hydrogen to hydrogen bonds do we have to break? 3. And what is that going to be? What's each one? 436. Okay? Minus bonds formed. We have, what's the only type of bond that's formed? The nitrogen to hydrogen. How many of those are we going to have? 6, right? And what's the value for the nitrogen to hydrogen? 391. Okay? So if you just want to make sure, again, this is your nitrogen to nitrogen triple bond. This is your your hydrogen to hydrogen bond. And this is your nitrogen to hydrogen bond. Okay? So you really kind of have to know the Lewis dot structure in order to be able to do these accurately. You have to know how many bonds you have of each type. So, when we plug all that in, delta H of the reaction what do we get? Negative 97. And that's just going to be kilojoules. So it's just a different way of calculating the exact same thing, the heat of the reaction. It's still really dealing with a potential energy, but this time in terms of individual bonds. We're just saying that how much energy to completely break every bond and then reform them in the new way. So let's look at one more and we'll call it a day. As we look at number 67, let's look at 67A. And for the sake of time, we'll just do this one all together. And that's going to be CH4 plus, what is it? Plus what? O2. Is it 4 of them? Is it just O2? And it's going to go to CH3OH? Okay. I knew there were some coefficients in there. All right, so we want to calculate delta H of the reaction. So we go and plug this in. We're going to go bonds broken. Well, the CH4, that's going to look like this. So how many carbon to hydrogen bonds are we going to have to break total if it's 2 CH4s? 8, right? So it's going to be 8 times the carbon to hydrogen bond, which is carbon to hydrogen single bond, 413. Plus, this is my oxygen to oxygen double bond. How much is that one? You guys got to talk louder. I just can't hear you. 495. Okay? Minus bonds formed. Now this time we're going to have CH3OH. We're going to have 2 of them. So these carbon to hydrogen bonds, how many of these are we going to have total? Since there's 2 molecules, we're going to have 6 of these ones total, right? And that's the same as this, so it's 6 times 413. Plus carbon to oxygen. We have 1 in the molecule, but we have 2 molecules, so it's going to be 2 times, and this is carbon to hydrogen. So what's the carbon to oxygen? Say it one more time. 358. Plus, now we have the oxygen to hydrogen single bond. And we're going to have 2 of those. Oxygen to hydrogen is 463. So this is my carbon to oxygen. This is my oxygen to hydrogen. And you don't need to label them on top like that, but I'm just doing that so you can make sure you know which one's which. So now you just plug all that into your calculator. Again, note, remember, this negative distributes to each one of these, so you might want to add this whole term up and then subtract it out. Use double sets of parentheses, however you want to do it. But what's the final answer? Then we're done. Three, two, one. Okay? I guess we can say 3, 2, 1, go. Because we're done. Does anybody have any questions? Does everybody understand where all the numbers are coming from? Now, in this one, obviously, you have to be able to do the Lewis dot structure. So to know how many bonds, what bonds are being formed, which ones are being broken. A lot of times on the AP, they'll give you the structure like they do in those problems at the beginning of the page. All right, you just have to be able to know how to plug in the values.